another conservation of energy and, turns out, momentum problem, all wrapped into one. Looks like this. There's a person over here at the top of a hill here, and they're going to run towards the right here with a speed v0, and they're going to jump onto a sled. And they've given you some parameters in the problem, like they've given you the mass of the person and the mass of the sled. And so what happens when they jump on the sled, of course, is this v0 here somehow translates into an overall speed of the sled and the person after they jump on there. So sort of in that case, after they jump on, you'll see the person on the sled now like this, and the person and the sled will move in this way, not necessarily with v0, but some different speed v, which we have to figure out. And once they have that speed v, they're going to go down this slope, and they're going to go in here and hit the spring, and we'd like to know how far do they compress the spring, because eventually what will happen is the spring will get all bunched up here, and the person on the sled or the ski will be all bunched up against the spring, and they'll be stopped. So we'd like to know what that is, how much the spring gets compressed. So this problem here just sort of involves some conservation of momentum at the very beginning here, because you need to know what this capital V is here. In other words, how fast is the person-sled combo moving after the person jumps on it. And you can get that from conservation of momentum. It's an inelastic collision up there, because if you want to think about it, the person sort of sticks to the sled, so they stick together there. So what I see in conservation of momentum, I see P initial is equal to P final, say along the x-axis right there. And initially what I have is I have the person running, the mass of the person times v0, and all that goes into the mass of the person plus the mass of the sled times that capital V. So there's your conservation of momentum. So I can get my capital V that way. And this will be the capital V, some number in there. This will be the capital V, or the velocity that the person-sled combo has when they leave this hill. Now what I have is a straight conservation of energy problem. I can now jump to conservation of energy and say, hey, to get this problem to work out now, I do E initial is equal to E final. And it turns out that if I look back at the picture here, the person at the very top of this hill here on the sled moving with speed V, this is the initial configuration of the system as far as energy goes. The final configuration will be all the way down here when they're in contact with the spring. So the way I'd set that up then is, okay, I'll say what sort of initial energies do they have? Well, they have kinetic energy because they're moving here. 1/2 m times the mass of the person plus the mass of the sled times that capital V squared. That's how much kinetic energy the sled person combo has as they leave the top of the hill. And they also have some potential energy because they're so high above the ground. And I'm not putting that right in the right mass there, am I? This should be mass of the person plus mass of the sled times G times H. So this is the potential energy of the mass-person combination here. And where's that H from? Well, the H is their straight vertical height above the ground, something like this and like that. There's their vertical height right there. That's how high they are above the ground. And that's their potential energy as they begin the problem here. So all of this is my initial energy here, and when I'm all done, all that will sort of go into some final energy state. Now if I look at what energies the system has over here, the person doesn't have any more potential energy because they're on the ground. They don't have any more kinetic energy because they're not moving anymore, but all that energy now has been transferred into a compressed spring. So I'll just say all that energy has gone into 1/2 times the spring constant times the delta S squared. That's where all the energy goes. So that in a nutshell should allow you to solve the problem for whatever they're asking for here, but just keep in mind once again, it's tracking where energy went. Here's their initial energy right here. This is their E initial right here. Kinetic energy at the top plus potential energy at the top. This term here is their final potential energy. And you should be able to solve for whatever is needed at this point.